Hello everyone, this is Dennis, and you're on the Electro channel. Today I want to try an unusual experiment. It involves taking a computer power supply and adding an additional transformer to it. This video is for informational viewing purposes only. I just wanted to show what I found interesting, what the outcome was, and I'm not forcing anyone to follow my lead. To better understand how I'm going to do this, you should use the diagram. Here's a simplified illustration of a power supply transformer with a rectifier. This is the primary winding, and this is the secondary. In reality, the secondary winding has more terminals, as it carries both 12 and 5 volts. Each of these voltages has its own capacitors, diodes, and inductors. But since we won't be messing with the operation of this transformer, I've drawn a very simplified diagram. The second transformer will be connected to the power supply very simply. We'll connect its primary winding in parallel with the primary winding of the transformer and the power supply. When the power supply turns on, current will flow to both transformers at once. This is what the transformer I'll add to the power supply diagram looks like. It has 9 terminals, 2 for the primary winding and 7 for the secondary winding. This bundle of several wires, called a braid, is the midpoint of the secondary winding. In the diagram, it's always shown as ground, but for ease of understanding, we'll simply call it negative. The transformer located on the power supply also needs to have its primary and secondary winding terminals located. My primary winding terminals are located here. Now we need to do the following. Take 2 wires and solder our transformer parallel to the first transformer. It's not necessary to solder the left contact to the left and the right contact to the right, as in the picture. Our current is alternating, so there's absolutely no difference here. I soldered my wires to the same terminals that the legs of the power supply transformer are connected to. This is what I got. You don't need to use very thick wires, but it's better not to use thin ones either, otherwise there will be a voltage drop. Now let's see if our new transformer works. First, I turn on the power supply through the safety light. Remember to do this every time, even after the most minor modifications. The light blinked and went out. That's how it should be. Now I take the negative wire and connect it to the green wire on the ATX connector. After that, I leave the circuit running for about 5 minutes, watching to see if any parts are heating up. Ideally, everything should be cool. Even though the transformers look almost identical, the operating frequency of their power supplies may be different. If the frequency of this power supply is significantly higher than the frequency at which this transformer was operating, it may heat up even at idle. To determine whether our new transformer is working or not, and whether there is any voltage at its terminals, we need to assemble a small circuit. This is a simple half-wave rectifier. For example, I used an FR107 diode, a 1 kilo ohm resistor, and a 400 volt, 10 microfarad capacitor. The negative terminal of this rectifier is connected to the midpoint of the transformer's secondary winding. Roughly speaking, the braid. A voltmeter is connected to the rectifier's output. Then, each terminal of the secondary winding should be connected in turn to the anode of the rectifier diode. This way, using the voltmeter, we can determine which terminal has which voltage. The diode needs to be high frequency and high voltage, but a low current one will do. It's also advisable to use a high voltage capacitor. Its capacitance should be between 1 and 10 microfarads. Now let's see what we've got and what we find here. As in the diagram, I've already connected the negative terminal of the half-wave rectifier to the wire harness. I place the probe on the first terminal. The transformer is working and even produces some voltage. The voltmeter shows 8.5 volts. The second terminal shows exactly the same. The third and fourth terminals show roughly the same. But the voltage at the last two terminals is much higher, almost 20 volts. This is very good, but also very strange. Why is the voltage at the terminals where there should be 5 volts, but it's 8.5 volts, and where there should be 12, it's almost 20? If anyone in the audience knows the answer to this question, please let me know in the comments. Now that I found the terminals where there should be 12 volts, but in fact there's much more, I can assemble a full-fledged rectifier. To do this, I soldered Schottky diodes to the terminals. This is an assembly of two MBR2100CT common cathode diodes, rated at 20 amps and 100 volts. I attached the diodes to a massive heatsink. Then I added a bank of capacitors with a total capacity of 1500 microfarads and soldered a 1 kilo ohm resistor in parallel. The voltage of each capacitor is about 200 volts, although you can use smaller ones of 100 or 63 volts. In the diagram, it will look like this. I soldered the new part of the circuit to the power supply, and now I also power it through a safety lamp. The power supply starts up, and the multimeter immediately shows 26 volts. This is the voltage from the secondary winding of our new transformer. Since our transformer has no feedback from the PWM chip, the voltage at its output is not stabilized. It will constantly fluctuate and depend on the input voltage in the load. Just like in a regular iron mains transformer. Now I'm removing the light bulb at the power supply input. Now the power supply will receive more voltage without it. And as you can see, the output voltage has also increased. It's now 27 instead of 26. To reduce voltage drop under load, I'll load the 5-volt line with a resistor. For this, I'm using a 5-ohm, 5-watt resistor. When it's connected, the voltage also increases slightly. Now it's time to test our new transformer under load. Here's the power supply. Here's the new transformer, and between them is the cooling fan. The multimeter shows the voltage at the power supply output, and this analog ammeter shows the load current. Off camera, there's an electronic load, and I'll be loading the power supply with it. The resistor on the 5-volt line isn't connected yet. I connect it, and the voltage rises slightly. I begin to increase the load. At 2 amps, the voltage dropped by about 2 volts. That's a little over 50 watts. At this point, I want to show how the power supply works without a load resistor. I'll disconnect it now and watch the voltage drop. The voltage dropped from 26 volts to 24 volts. And with further load without this resistor, the voltage will drop even further. Therefore, in such cases, it's always better to work with it. I continue loading the power supply. As the load increases, the voltage also continues to drop gradually. 25 volts 4 amps is 100 watts. almost 24 volts, 7 amps. 170 watts, a pretty good result. At this power, the power supply doesn't heat up much, but for some reason, the new transformer starts to heat up very quickly. Moreover, it feels like the primary winding, which is located on the outside, is heating up. It's possible, of course, that the issue is the thin wire of the primary winding, although the transformer doesn't look that small. Although it's possible that the secondary winding also heats up, since I'm loading a 12-volt line. And in such power supplies, it's usually rated for 8, 10, or 12 amps. In general, during testing, I found that the optimal current for such a transformer in this condition is 5 to 6 amps. So the transformer doesn't heat up much. But I don't rule out that if the transformer were larger and used with a more powerful power supply, it would heat up less. But for short periods, you can increase the load even more. For example, right now, 8 amps at 23 volts is 185 watts. As you can see, the experiment was a success. 2 transformers from one power supply work well. And thus, we were even able to obtain decent power at a voltage of over 20 volts. Although, of course, it's bad that the voltage drops significantly under load. Also keep in mind that there is no short circuit protection anymore. More precisely, everything works exactly the same on the standard power supply lines as before, but the wires coming from the new transformer must not be shorted together, otherwise an explosion will occur. Therefore, be very careful when working. However, this method is still quite suitable for powering some light bulbs, motors, or audio amplifiers. If they require more than 20 volts to operate, and all you have on hand is a computer power supply. That's all for today. Like, subscribe to my channel if you haven't already, ask questions in the comments if anything is unclear, and bye everyone.